going to start a bit of a series on chemistry because I think chemistry is really cool and important. And I'm going to be using this book right here, Chemistry by Zumdahl and Zumdahl. I think they're. Did I misspell their name? Oh, I did. There should be an H. I'll fix that. I think this is the chem textbook they use for intro chem at University of Illinois. These two people came from University of Illinois, Steven Zumdahl and Susan Zumdahl. So maybe they're just promoting maybe this is U of I propaganda. But I'm gonna use this book to follow along with the the chemistry to learn chemistry. This is the book I'm gonna use. So this first chapter, it's chemical foundations. It's you don't like if you want to learn chemistry. My chances are you pretty much know this stuff. So you don't have to watch this video. I'm just gonna go over each of these topics really quickly. There's a thing from the book that I like, which is kind of like the two foundations or kind of foundational ideas of chemistry. And it's the idea that, one, all matter is composed of atoms and changes occur when atoms reorganize. This is pretty much the two big ideas from chemistry. Chemistry, it's the study of matter, and it's the study of how matter changes, right? So if you think about one example in the book they use is gasoline. Gasoline, it's composed of atoms. I don't know exactly what gasoline is made of, but it's composed of atoms. How does it make your car drive? Well, you need an engine, a 4-stroke engine, and the gas will combust, right? Combustion is just the reorganization. It's a reaction. It's the reorganization of how those molecules of gasoline as well as oxygen, and right. Oh my goodness, I'm forgetting combustion reaction. Wait. Yes. Oxygen and gas, forms of combustion reaction, and then out of it you'll get some carbon dioxide, a little bit of water, right? It's the reorganization of the atoms in the gasoline that causes the change, which would be the gas suddenly expanding and combusting, right? This is the idea of chemistry, and that's what makes chemistry so cool. Is you can look at how do these things change, how do molecules change. When you eat glucose in your body, glucose has 6 carbons, 12 hydrogen, 6 oxygen, right? It's going to, when it enters your cells, it goes through glycolysis, and that carbon dioxide will eventually turn into that glucose will change, its atoms will be reorganized into pyruvate. And by the time you get pyruvate, you're gonna get some NADH, and yeah, my biology is really, I believe you'll get NADH, which will then later be oxidized to reduce oxygen into water. And the point is, that whole process will eventually give you ATP, adenine triphosphate. It's this reorganization of atoms that causes change because of energy and catabolic anabolic reactions, and it's really such a driving process for this world. Chemistry is so important. It's what calculus is to physics is kind of like what chemistry is to biology, right? A lot of biology is governed by ideas of chemistry, and ideas of chemistry are really driven by ideas in physics. So that's kind of one thing that in this course it's not really a course, it's just me explaining chemistry. But in this little video series, as I go through this book, I want to show just how all of these ideas of science are really interdisciplinary. That's kind of, I guess that's my overview of chemistry. Maybe not what the book explicitly stated, but that's my overview of chemistry. The scientific method, you probably learned it in middle school. It's just the idea that science is really observational. right? We kind of lose this in physics, especially if you've taken a lecture-based physics class. You kind of, you're so absorbed in like these like a theoretically frictionless plane that has no friction, and elastic collisions, and non-compressible liquids, right? Because liquids we treat as usually incompressible. So sorry, did I say compressible fluids, right? Usually we say they're incompressible. And I think actually, I don't know if fluids are, or I don't know if liquids, actually a compressible liquid, a non-compressible liquid is actually probably good, but like, you get what I mean. We make all these, assumptions because it's a lecture-based class and you're solving problems. But really science is about observation, right? These approximations we make in physics are just a result of we've ran a lot of experiments. And in the experiments, we found out that, when two cue balls hit, it's actually usually pretty elastic, right? So that's an assumption we make. Well, that's from observation, right? And observations can go, they can go pretty far. You have these observations, you make a hypothesis, right? That's one step of the scientific method, is you make a hypothesis, make a prediction based off your basic observations. What do you think those observations are saying about the world, right? Making a hypothesis will then lead you to an experiment. Now you have these you have your initial just observations. You made a hypothesis. Now you need an experiment with actual constants being held, only changing one independent variable in order to measure a dependent variable, right? Independent variable being kind of the thing you want to test, dependent variable being like the effect you're measuring, right? So if I have a hypothesis that, my plants will grow with this specific type of water like mixture, like maybe if I add nitrogen to the water, it might make the plant grow well. I mean, that's it's a somewhat reasonable idea. So make that your independent variable. What type make your independent variable the type of water. Does it have nitrogen or not? And then the dependent variable can be what you grow, right? So these things are part of the scientific method. And with the scientific method, maybe you realize, wow, adding nitrogen to water does make my plant grow taller, right? Well, that can you can kind of use that as sort of a I guess I should say that's where laws and theories come from. I can make Krish's law of my specific plants, that when I have this specific plant, and I add nitrogen to the water, it'll grow taller. With this specific plant in my like house, right? I can call it Krish's law of his plan. It's like, I don't know, like that a law is sort of these summaries of these general ideas. It doesn't explain why it grows taller, but you can make this law to help essentially predict that, now when I have this specific type of plant, let's say a tulip, and I add nitrogen to water, when I water it, it'll grow taller, right? Now, what scientists do, that's kind of a lousy law, because that only works like with my plants in my house. Scientists will run a lot of experiments to be like, will it work on this type of plant? Will it work on different types of plants? Would it work if I went to an environment that had like low air pressure? Like if I go to the Mount Everest, will my idea of adding nitrogen to water, causing it to grow, will that still work, right? And through these experiments, you can make general laws, right? Newton's first law is pretty excellent because it works in quite a bit of environments. Now, I think Walter Lewin said that, Newton's first law, Newton said, okay, let's do Newton's third law. Newton's third law, that's such an excellent law because we've tested that in a lot of different, scenarios, right? That, Newton's third law holds in so many scenarios that we're very confident in Newton's third law. We've tested it in so many scenarios that we're pretty confident that it's just going to work in general. And we haven't found evidence that disproves that. Probably, maybe. I don't think we have. Maybe we have, and it's some weird quantum mechanics thing. But I'm not that knowledgeable, but you get what I mean, right? So the more experiments you run, the more you can. If I have this plant with my nitrogen water idea, if I try it with other plants, oh my law is kind of growing. A theory explains it. I have no idea if nitrogen water does anything, but if it did, let's just say I could develop a theory or a model that explains why. Maybe there's a certain metabolic reaction going on in the plants that when I add nitrogen, it boosts it. It's not a reasonable idea. Nitrogen's used for DNA. Nitrogen is a component of amino acids and therefore proteins. It's not a terrible idea that thinking, oh, maybe adding nitrogen to water will somehow make it work, right? So I could develop a theory based off of that. That's kind of the idea of scientific method. Okay, I'm gonna just buzz through some of these since units of measurement, you kind of already know. Kilograms for mass, meters for length, seconds for time. This is called the SI system, International System of Units, but it's French, so it actually goes Sistema Internet. I don't know, you get what I mean, SI units. Joules. Well, joules is not really a unit. Well, it's a name for a unit. Really, 1 joule, if you know from physics, that's a unit of energy. A joule is just a kilogram meters squared per second squared. I'm sure there's a name for like these fundamental, like kilogram, that's fundamentally mass. Seconds is fundamentally time. Meters is fundamentally length, right? Joule, it's not like a fundamental thing. It's a composition of those other units, right? So I'm sure there's a name for those fundamental units like kilogram, meters, seconds. But with joules, then you can get, like coulomb is like sort of a fundamental unit of charge. Joules per coulomb, right? Joules over coulomb, well, that just becomes volts. Well, joules per coulomb, that's kilogram meter squared over second squared per coulomb. So a volt is really all of those fundamental units. A volt is the unit for electric potential, if you're unfamiliar. So that's the idea of units. Uncertainty, units of measurement, there's uncertainty in your measurement. You're never going to have a perfect scale to measure mass. It's going to be a little bit off depending on its accuracy and precision. Accuracy is sort of like how actually accurate. So like if I'm shooting a bow, if I'm doing archery and I'm hitting the bullseye, like I'm hitting the bullseye a lot, or around it pretty close, I'm pretty accurate. But let's say I'm like if I have my my little bull, or I don't know what you call this, target. Let's say I'm hitting like all my shots like right here, like consistently. I'm pretty off, right? Like versus something like this. Like I'm pretty off, but as you can see, I'm hitting pretty much the same spot. So this is called precise. If you're precise, doesn't necessarily mean you're hitting where you're supposed to be, but you're hitting wherever you are hitting, you're hitting it pretty much on the money every single time, right? Precisely wrong, I guess you could say. Accurate is, you're hitting like close to where you're supposed to be hitting, but there's a bigger spread. You're not hitting exactly that same spot. Significant figures, there's actually quite a bit of rules for significant figures, but I think the general consensus is if you have it in decimal form, right, like 0.00, you're just looking at, what are the numbers that actually tell me, because the 0.00, it does tell me information in the fact that, this gram, reading, like it's very small mass, but I guess the significant figures are like the numeric, I don't know, it's like, I guess the information, it's kind of hard to explain. Significant figures, I guess it's just rounding. It's just like how much are you rounding, right? This has 3 significant figures. Let's say I rounded this instead of 0.00105. Let's say I rounded this to 0.11. Well, I'm losing a little piece of information there. There's only 2 significant figures because I kind of rounded, and now it's like, I'm not this could be 0.106 or 0.107, but I'm kind of losing that information when I round. So this had 3 significant figures. Now it has 2. Right here, I have 5 significant figures. This 0 does count. It's some rule about 100 only has 1 significant figure, which I guess seems reasonable, right? I guess if you're either right, there's just a 1. But if I add a decimal at the end, now this becomes well, I don't know. I think this point will be 3 significant figures just by adding a decimal. It's a kind of a bizarre rule. This has 4 significant figures. This is the cleanest look. Scientific notation. Times 10 to the negative 3, that's, as you're familiar, just moving the decimal back 3 places. So this is really the same thing as 1.1 times 10 to the negative, let me just think, 3. It's 1.1 times 10 to the negative 3. So this we can very clearly say, oh, 2 significant figures. I don't even have to worry about the zeros, right? Now this is kind of weird. 1.00 times 10 to the negative 3. This is 3 significant figures, right? I've rounded to the 100th place, right? This gives me more information than 1 times 10 to the negative 3. Because 1 times 10 to the negative 3, that could be 1.01. This could be 1.4, right? Based off how I round it. So significant figures, I guess, kind of tell you the degree of information you're getting in terms of your, precision of the calculation. 1.6, learning to solve problems systematically. It's the idea of solving a Rubik's Cube, right? I think most amateurs at solving Rubik's Cubes, if the red side is almost completed, they're not gonna goose chase and just try to solve the red side. You know what I mean? If you have do I have a Rubik's Cube? If you have a Rubik's Cube, let me just make sure this thing is recording, by the way. Okay, good. If you have a Rubik's Cube, generally we're taught solve the white face, then solve the first layer, which, okay, let me just draw a Rubik's Cube really quickly. This is kind of becoming a long-winded point on something people don't really care about, but so when you have a Rubik's Cube, we're taught solve the first white face, then solve this first layer, then the second layer, and then the third layer and the yellow face, right? Like there's a systematic approach. People who don't know how to solve Rubik's Cubes, what they'll probably try doing is they'll see, oh, the red face, let me just draw like, oh, the red face, oh, it's so close. It's so close. I just need these 2 pieces. Let me try to goose chase and try to get these 2 pieces. They're usually not going to do that because in the process of doing that, you're going to mess up the red piece, right? You need a systematic approach, right? Don't just goose chase and try to find answers, because then you'll get lost and you'll mess up the red face. If you have a physics problem or a chemistry problem, write down what are your unknowns, what are your knowns, and think of a systematic way of, oh, even though the answer might seem like I should do this, I know through practice that, I should probably start with writing down my general equation and then writing down, plugging in variables. It seems a little bit slower, but you're going to get a more systematic approach. I guess that's kind of the idea of this. Dimensional analysis, it has to do with units, right? So if you didn't know, 1 inch is about 2.54 centimeters. So if I divide by 1 inch on both sides, or let's do if I divide by 2.54, because of this equality, then therefore, 2.5 over 2.54, that just becomes 1. So this ratio is what we call, so 1 inch over 2.5 centimeters is just equal to 1, because these both are fundamentally the same, measurement of length. This is what we call a unit factor. So just like how I can multiply 1 onto any number without changing it, I could multiply 1 inch over 2.54 centimeters onto any number without changing it. And this will get into stoichiometry later on, but let's say I wanted to convert 3 centimeters. Well, I could multiply it by 1 inch over 2.54 centimeters. Why would that be useful? Well, hey, the centimeters are essentially going to get canceled out. And now I just do 3 times 1 over 2.54, or 3 divided by 2.54. So maybe, I actually don't know what that would be. 1.25. I'm not actually exactly sure what it would be, but it'll be 1.25 inches. I don't know when I run that in my calculator. And that's kind of the idea of dimensional analysis. Temperature it's I guess a measure of the amount of average kinetic energy. So if this book has a certain temperature, well, its molecules are moving at a certain speed. So the temperature kind of reads the average kinetic energy of all the movement of molecules. This is kind of like something we'll explore later on. You don't need to worry too much about it. Density, how compact things are. So the equation for density is rho equals m over v. So this is the thing in physics, right? Like we do these problems in physics where it's like, oh, let's say we have a ball that we roll down a ramp with 5 centimeters of radius, right? Now suppose we took another ball that had 10 centimeters of radius, but the same mass. That's kind of a confusing idea because it's like, oh wait, my ball is bigger, but it has the same mass. I thought when I make something bigger, it'll usually increase in mass. And generally in the real world, that's kind of the case because of density, right? If I have Play-Doh, if I have a Play-Doh ball and I add more Play-Doh, well, yeah, I'm increasing the volume of my like little Play-Doh sphere that I'm making, and because of that, it's gonna increase in mass because now the density is the same. If I have Play-Doh, I'm adding mass to it, so the mass should increase. And by how much that mass increases, well, it's based off the density, right? If I want to add a pound, why is that like a pound of bricks versus a pound of feathers? If I add a pound of bricks to something, I only need like 1 or 2 bricks. If I want to add a pound of feathers, I need to add so much because it has such a low density. So low density just means it's the matter is not as compact and dense. I think that's hopefully intuitive. And then there's classification of matter. I think in middle school we learned there's like 3 stages of matter. So there's phases: liquid, gas, solid. There's plasma, which I believe is charged gas. I don't know too much about it. Maybe throughout this book we'll learn more about it. Is there anything to say? That's kind of the idea of like physical versus chemical changes, right? A physical change to a substance. Oh, there's also something called a pure substance. Pure water is a pure substance because when you have a glass of water, it's only made of H2O. It's just H2O molecules. Sugar or table salt generally is considered pure substances because table salt is made up of the same thing, which is NaCl, right? Sodium chloride. Same thing with sugar. It's usually just C6H12O6. That's if it's glucose. I guess maybe it might be something more like, I think actually, like sugar, I think is not glucose. I think it's others. Whatever, you know what I mean? It's just the same molecule altogether. But a mixture is something like air. Air is a mixture of O2, N2, a little bit of carbon dioxide, a little bit of methane, right? Our atmosphere is this big mixture of stuff. So that's another terminology. This has been Chemical Foundations, probably stuff you know, but I wanted to get like a holistic, complete, like through my videos, I guess I wanted to cover every part of this book. So I just thought I'd make a video. But yeah, thank you for watching. I'm gonna stop recording right now because I gotta learn how to edit these videos one day so these endings aren't so awkward.